In today's lesson, we're going to be exploring the first ways that we can start to draw information from data that we collect. And in particular, we're going to be thinking about mostly pictorial ways of doing this, right? And so how can we use graphics to start to summarize data, right? And so this is for the process of describing what we've observed within statistics. So with that, we can get started. And the general overview of what we want to talk about today is to define what we mean when we're talking about the distribution of a data set. And so introduce the concept of a distribution. We want to understand some of the mathematical notation that we're going to be using throughout this course. And then we're going to take a look at some different visualizations. And we want to both explain what the purpose of visualization is, and also interpret and explain stem and leaf plots, dot plots, and histograms, right? So three common types of visualizations. The problem that we're addressing with these topics today is that raw data are effectively useless for interpretation. And so what do I mean by that? Well, imagine that I hand you this data set here, and I asked you to make some inference about it, right? I asked you to describe what's going on in it. Right? And if you're just staring at what's happening here, I'm quite sure that you're not going to come up with super meaningful insight. And that's because looking at data like this does not give us any useful information. Right? So remember that in statistics, what we're trying to do is gain useful information about a population based on our sample. And so instead of looking at raw data, what we want to do is start to try to summarize that. And one of the ways that we can do this is graphically. We can also use tables, we can use statistics, which we'll talk about more on. But one of the first ways that we can think about doing this is through graphical representations or visualizations. When we use graphical displays, what we're trying to do is summarize the useful information and present it in a way that we can digest it and determine what should we be doing next. Now, before we can look at those visualizations, we have to try to think about what is it that we're trying to visualize. And the central quantity that we're going to be talking about throughout this course is what we would call the distribution, right? And so we can think about the distribution of a data set to describe all of the possible values that are in the sample and how frequent each of those values are, right? So the relative frequency of each of those values. And so if you take this combination where you've enumerated all of the possible values and you say what proportion of them fell into each of the different buckets, that's what we're going to say is the distribution of a data set. Now, for notation, we're going to think about having n observations, right? And so we might have sort of a small n equals 10. You could think about n being a million, right? But in general, we're going to say that n represents the number of observations, and we're going to denote each of these observations with a lowercase x. Now, we will use subscripts to enumerate through the sample observations. So if we're just talking about an arbitrary observation, we'll use xi. And if we want to sort of enumerate all of them, we can use x1 through xn, right? So x1, x2, x3, and so on. Oftentimes, we're not going to think about these as having any particular ordering. Maybe they're ordered by when they were collected, or you sort them by some sort of random identifier. Other times, we might actually sort them according to the values. But generally speaking, we're using lowercase x's to denote these observations. Now, with that sort of notation out of the way, we can think about what are we hoping to do with visualizations? And there's several different goals that we might have when we set out to visualize a data set. And so maybe what we're trying to do is identify what is typical in the data, right? If we have a bunch of different observations, maybe we have, very high n, we want to know on average sort of what's happening, right? So we can use that visualizations to describe that. We can also think about how spread out are these data, right? So what's the lowest value? What's the highest value? And sort of how do we disperse the data throughout that range? We can determine if there's any gaps in the data, right? And maybe this is for the process of discerning, was the data collection good? But it's also, Are there sort of particular values that we might maybe expected to see that we're not seeing, which might be interesting to us? Or maybe we are seeing values where we wouldn't have expected to see some, and maybe that's interesting to us as well. We can try to determine what the shape of the distribution of the data is, right? And so, we can look at how flat it is, how curvy, are there different peaks, right? All of these different concepts are easy to see when we're visualizing the data. On the shape of the distribution, we can see where there's the peaks, what values are the most common, which ones are the least common. And we can also use this to determine if there are any outliers, any data points that look like they don't belong in the data set. Now, I'm going to make a point on outliers right here, and this, again, may contradict some of the information that you see in introductory textbooks, but I think it's important, so I'm going to emphasize it. While we will often look at statistical tools for detecting whether something is an outlier, it's very important to not assume that something that's an outlier in a statistical sense is a bad piece of data, right? Oftentimes, you're going to see people say, look at what outliers exist and then remove them from your data. And I'm here to tell you, you should never delete outliers from your data set. Now, anytime that there's a rule that's set out that's as strict as never delete outliers from your data set, there's going to be exceptions to that. But I can tell you that as a practicing statistician, I've never come across a scenario where an outlier should be deleted from the data set. I know that they exist. If you were measuring speeds and something went faster than the speed of light, right, maybe delete that one from your data set. But short of values which are physically impossible, you really should be keeping them all. Now, we still might want to see what are the values that are outliers, and maybe we want to do something about those values, but I'm here to say that that's useful information. So that was, a side tangent that's not particularly relevant, but we can use visualizations to detect where the outliers might be. So the first type of plot that we're going to be looking at are a stem and leaf plot. And this is not going to be a visualization in the way that you normally think about it. But the idea is that if you have some univariate data, right? So I just have a set of numbers here. Who knows exactly what they represent? But looking at this list of numbers is clearly not the most helpful, right? And so you could think about maybe what we could do instead is order them from smallest to largest. Right? And that will give us a little bit of a better sense. But then, even still, it's going to sort of be hard, and we won't necessarily see where things are clumping up. And so a stem and leaf plot is one way that we can approach solving this issue. And so what do they look like? Well, the stem and leaf plot look like this lower plot down here, right? And so what are we looking at? Well, on the left-hand side of the bar, we have the different starting digits, okay? And on the right-hand side of the bar, we have the different ones digits, right? So if you think about sort of this data set, right, we can see just looking at it, the values ranged from 0 to 50, right? Approximately, they're on that range. And so if you think about listing the tens column and the ones column from each of these numbers, you could break them up into separate observations. And the tens column is either going to be a 0, a 1, a 2, a 3, a 4, or a 5, right? And then the ones column is going to be somewhere between a 0 and a 9, okay? And so all a stem and leaf plot does is you first sort your data, and then you break off your leftmost digit, and you place that on the left side of a bar. And then on the right side of the bar, corresponding to each of those digits, you place in your rightmost digit, okay? And so in this case, when I start reading this off, starting from the top row here, I can see that I have a 0, 1. So that means that there's a 1 in the data set, right? And then I have a 0, 2, which means that there's a 2 in the data set. And then another 0, 2. So there's a second 2 somewhere in the data set. A 0, 3, 0, 4, 4, 4, 4, right? And so on. You can go down to, say, where the 4 is, and you can see that we have a 40. Actually, we have 4 40s in the data set. And then we have a 41, a 44, right? The way that it's visualized here, we're splitting the low ones digits from the high ones digits. So sometimes you'll see that, right? We have 2 rows for 0, we have 2 rows for 1, and so on. And you don't need to do that. It's going to depend on the data that you're showing. So if here we actually had digits that went up to 100, then we might instead list all of the zeros on one row, all of the ones on one row, and so on. The other important piece of information that's given is where it says the decimal point is 1 digit to the right of the bar, right? And so what we know is where are we going to be placing that decimal marker, right? And this isn't important for our data set because we know that these are just whole value numbers between 0 and 50. But if you didn't know that, then this is going to allow you to reconstruct your data set. So if we want to go through the process of constructing a stem and leaf plot, the first thing is going to be identifying our stems, right? So those are going to be those leading digits that we saw on the left-hand side of the marker. And then we need to identify what we call the leaves, the remaining digits, right? So everything that was on the right-hand side. We're going to place our stems from the smallest to the largest down in a vertical column. And then within each stem, we're going to place each leaf corresponding in ascending order, right? So we've sorted them in ascending order as well. And then we indicate what units we're working with. So where is the decimal point? And really all a stem and leaf plot is a different way of showing the whole data set, right? So you can go from a stem and leaf plot to the data set directly or vice versa. And the idea is that it's a lot quicker to look at our stem and leaf plot and determine sort of where are the values falling than it would be if we're just looking at the numbers, right? So we can sort of scan down the side here and we can see that there's looks to be approximately sort of evenly distributed numbers, right? There's no gaps that we're noticing. There's a few places, so say the low 30s have fewer observations in it than some of the other spots. But for the most part, you can see it's pretty evenly distributed here. And it's a lot harder to tell that if you're just looking at the list of numbers. So that's sort of the goal with a stem and leaf plot. A dot plot is in some sense similar, except it's a little bit more visual. So the idea is that we can take a single axis, right? So here we have the values 0 through 60. And then all we're going to do is draw a dot everywhere that we have an occurrence of a data point, right? And so again, that first value is a 2, and so we can draw our 2 in for that value, right? And so here, what the data that we're actually plotting represent is the where did whistles occur during a 60-minute NHL hockey game, so the proportion of that, right? And this is just a subsample from a single observation. And the idea with our dot plot is that, again, we can scan pretty quickly to see where are these values actually coming up, right? So if we look at it, again, we can see that there are a few peaks, there are a few more spaces where there's no values being observed, but for the most part, we're not seeing there sort of being a large lumping around any particular value. So in order to construct our dot plot, we will plot all of the observations on a vertical axis at their value. Whenever we have a single observation appear more than once in a data set, we start stacking them up. So you can see in the different piles right at 40, you can see that there's more observations than there are sort of at other points, right? And that's how we construct a dot plot. It's a very simple way, again, of just fully summarizing the data. We can go directly from our dot plot back to our data set. You could take a data set, derive a dot plot directly from it. The last type of plot that we want to look at today are called histograms. Now, histograms are going to represent our frequency distribution by using bar charts, right? So we're all sort of familiar with bar charts from just our day-to-day life. Histograms are a particular kind of bar chart. With a discrete variable, we're going to use each of the categories and count the number of observations that we have in each category. When we have a continuous variable, we're going to bin the observations and then count the observations in each bin. So we're going to decide on different breakpoints and then count how often do they show up in each of the bins. We can also use the relative frequency rather than the count. And so that would be given by the count in each of the bins or in each category divided by the total number of observations. So it's the proportion here, relative frequency and proportion, the same idea. So this is what our histogram looks like. And so here what we're plotting out is the length of penguin bills in millimeters, right? And so you can see that we're using a count along the y-axis here, and along the x-axis is the actual value. And so you can see that for each of the millimeter values, we have sort of different values showing up, and the bar heights represent how often did that occur. And so you can see this is a little bit more visual of a way of getting to what the distribution might be, right? Some points about the different widths of the bins or the classes. So we want them to all occur with the same width. This is particularly relevant if you're doing a continuous variable, right? So where you break up the different classes, we want them to be the same width. We also want them to never overlap. So in a histogram, each count should only fall into one category, right? You shouldn't be able to put something into two categories. And the classes should cover all of your possible values, right? So everything that's observed in the data set should be plotted on the histogram. And so if you do that, then you just count up your relative frequencies or your frequencies directly, and you get to your histogram. And so if we think about sort of looking at the way that we would construct this histogram, right, we can think about having, say, fixed a number of bins here. So in this case, we would say that, say, the lowest value that we've observed is going to be a 30, right? The highest value that we've observed is going to be a 60. And maybe we want 6 different bins, right? And so then each of the bin, we're going to have a bin size of 5. Okay. We can go through and we could count up how often did each of these bins get observed, right? And so that's where you can see we have our 11, we have our 89, we have the 77, and so on, right? And we could plot our histogram using those counts. If instead of those counts, we wanted to use a relative frequency, then what we're going to need to do is sum up all of those values, right? So we'll have 11 plus 89 plus 77 plus 113 plus 47 plus 5. And then we're going to take each of those values and divide by that, right? So the relative frequency for the first bin, and so if I just say bin 1, is going to be given by 11, and we're going to divide that by 11 plus 89 plus 77, 113, 47 plus 5, right? And if you do this calculation, you should see that it's 0.006432749, right? And you should be able to do that for all of the different bins that we have here, right? And if we actually then plot this out, you can see that we get this sort of different looking histogram. It's of the same data that we were looking at before, but here we have these sort of fixed width 5 interval bins, right? So we're using the frequency. We could also be using the relative frequency. Now, when we're looking at a histogram, we want to include sort of the shape of the distribution in our considerations, right? And so maybe we're thinking about modality, right? What are the different peaks of it? We could be thinking about symmetry, right? And that could be symmetry around a value, symmetry around 0. And we might be thinking about the skewness. Are most of the data small or most of the data large? So modality refers to how many peaks or modes there are. If we only have one peak in the distribution, we call that unimodal. If there's 2, we call it bimodal. If there's 3 or more, we're going to refer to that as multimodal. If the distribution sort of looks like it could be a mirror image of itself, we say that it is symmetric. If it's not, then we're going to say it's skewed. So distributions are all symmetric or they're skewed. If our distribution has what we would call a negative skew, then its tail points off to the left. If it has a positive skew, then it has a tail pointing off to the right. This can be a little bit confusing. So if something has a negative skew, most of its values are going to be closer to the positive. If it has a positive skew, most of its values are going to be towards the negative. And we'll see some examples of this. We also might think about where the center of the distribution is, right? So what value is sort of the most typical? And we might think about the spread of the distribution. What are the total range, how much of the distribution occurs within specific ranges, and so forth. Again, think about outliers, but I will caution you in the same way that I did before about outliers. So we can take a look at several different examples here, right? And so we're thinking about looking at this distribution and trying to determine sort of its shape, its symmetry, and so forth. So we can see that for the most part, this is a distribution that is symmetric around 0, right? If you sort of mirror the distribution on 0, then you're going to sort of see the same thing on the positive or the negative side. There's not a particularly noticeable skew. We see that there are a few values down by -3, more so than there are up by +3. But that's a fairly minor difference, right? You might think about all of those values down at -3 as sort of being outlier type values, right? There's only one mode in this distribution, right? You can see that it sort of all peaks up to being around 0, right? We don't see other sort of peaks that are the same way. The spread on the distribution is about from -3 to +3, but we can see that most of the values are going to fall, say, between -2 and +2, and even going as low as -1 to +1, we're going to have, a large portion of the values in there. Okay. If we compare this to the next histogram here, evidently here we have a skewed distribution, right? And so what skew do we have? Well, we have our tail of the distribution pointing off to the right? Where the tail is going up to the right. And so we say that it's right skewed or positive skewed, right? And so most of the values are going to be low here. The most common value is going to be around 0, right? So it's still unimodal here. But this time you can't sort of mirror around it. The common values are all going to say be between 0 and 1 or 0 and 2. But we can see that it goes way higher than that, right? So the range of the values is going to be up to over 6. But you can see that once you're up into that tail up there, they're all sort of looking a lot more sparse, right? Most of the data is going to be beneath 3 or even beneath 2. Okay. If you sort of flip that around, now we have an example of a left skewed distribution or a negative skewed distribution, right? And so here, again, our most common value is going to be about 50, but we see that the tail goes off in the opposite direction. So you can think about this as being unimodal as well, non-symmetric, so forth. This final distribution is a little bit more interesting to look at maybe. So the first thing to note is that it's bimodal, right? There are two obvious peaks, one of them say around 3, one of them around -3. But it's important to note with this distribution that we still do have symmetry, right? If you mirror things around 0, the distribution's the same on either side, roughly speaking. It's just sort of each of those is going to have a mode in and of itself. And so we have a symmetric non-skewed distribution. In some sense, you could think about the spread of the distribution as being, -6 to +6. But it might also make sense to think about the spread as sort of being, there's one part of the distribution that goes 0 to 6, right? And that seems sort of separate from the part that goes -6 to 0, right? So you can start to sort of break down the nuance there. If we think about what are the most typical values, well, you could be thinking about those as being, plus or -3, but in some sense, we could also think about that as maybe canceling out, right? And so thinking about if you're going to take repeated measurements from here, maybe you're expecting them to be around 0 on average, right? And so you can sort of read all of that from our histogram. This example here is different from the others in that there's no obvious peak, right? We can obviously say that, say, just beneath 0.6 is the highest value, but that doesn't really stand out to our eyes as being obviously higher than anything around it, right? So it's almost a uniform type distribution here. Again, we're sort of seeing a symmetric distribution. The range here between 0 and 1, it doesn't really make sense to think about a further breakdown on that spread because values look approximately equally likely across the whole range. You could also think about comparing multiple histograms and thinking about how the distributions differ there, right? And so here, what I've done is I've separated out the build depth from 3 different types of penguins and plotted the histograms on each of them. Right, and so we can see that each of them are approximately unimodal distributions. The leftmost distribution here maybe doesn't look unimodal, but if you sort of think about smoothing this out, sort of the peaks are all around the same, right? But it's going to be sort of maybe symmetric. Maybe there's sort of a tail that goes up to the positive values, right? The middle distribution's a lot more uniform, though, right, than the other two. The other two sort of tail off. The chinstrap penguins appear to have a far more uniform values, right? You can think about their different ranges. and so forth. Right? So putting multiple histograms beside each other would allow us to compare the distributions a lot more easily than if we were just looking at raw data. If we want to look at histograms when we're using categorical data, then what we do is we first refer to this as a bar chart, right? So we're all probably familiar with bar charts. The other thing that you'll notice here is that we've separated out the bars, right? So if we go back to the penguin build up here, we're pushing all of the bars together. There's no space between them. And that's to indicate that we're dealing with continuous numeric data. With categorical data, we do this sort of separation. And so here we could think about how many penguins exist for each of the different species that we're including in our data set. And you can see that there's more Adelie penguins than there are chinstrap or Gen 2, right, in the sample that we have. Right, and so a histogram on categorical data is referred to as a bar chart, and just remember that we sort of separate it. In summary, raw data, they're difficult to interpret on their own. So instead of trying to work with raw data directly, we turn towards visualizations. And visualizations can help to display the character of a distribution, right? So you can walk through the different visualizations and start to pick out what are the important features of that distribution. We have stem and leaf plots, dot plots, and histograms that we looked at, and they're all useful for quantitative variables. We can also use histograms when we consider them as bar plots to categorize categorical variables, or to display the distribution of categorical variables. And so we're going to see lots of visualizations throughout this course, and so hopefully you can become familiar with these different types. That's all that I wanted to talk about in this lesson, and so I will see you in the next one.